So far, we've really categorized reactions as from the perspective of enthalpy, which is a really important factor in the transfer of energy in chemical systems, because it takes into account the energy of the changing bonds breaking and forming, and it also accounts for PV work in the system. Um, and we've thought about those systems as either a net delta H of negative, where you have a sort of a downhill reaction in terms of the enthalpy. So we go from reactants to products, and we release heat, and that's why we have a negative delta H. Or we have this uphill process, which means we need to put heat into the system from the surroundings. Um, and that's a really good way to think about things, but it's not the full picture. In order to fully understand whether or not a chemical system is going to proceed without any external influence or is going to require some external influence, we need to introduce this concept of entropy. And entropy is the key to that question, whether or not some chemical process will be spontaneous or non-spontaneous. So spontaneous in the chemical world means something that will occur without external influence. It's just going to go and run. Non-spontaneous means that some input is required to get that reaction to run. All chemical reactions can be categorized as either one of these. It's a binary thing. So you're either spontaneous or you're non-spontaneous. But we need to consider the contributions of enthalpy to spontaneity, as we know and we've defined, but we also need to consider the contributions of this thing, entropy, which we haven't talked about yet. So entropy is this really interesting and sort of cryptic physical quantity, but in this context, we can think about it as molecular randomness, and that's a little bit of an oversimplification, but it will be fine for the types of discussions that we're going to have in this class. In Chem 108, you'll introduce this a little bit more. One thing you can state, just as we'd said before, that the universe always strives to lower the energy of the system. That's true. Sort of second tenet is that the universe always strives to increase molecular randomness. So all things in the universe, this is a tenet. This is trying to occur around us all the time. And the example I often like to give when I'm teaching this class is think about your dorm room. Think about the room you're in right now. Think about any room that you've lived in the recent years, and think about the work that you have to put into that space to keep it ordered, to keep it not from becoming random. That's what entropy is, right? If you just let a system go, eventually it will proceed towards randomness unless you put energy into the system to get it back to order, right? That's why we clean our house. That's why we clean our rooms, and we organize our desk, and we organize our mind and our lives, is because all things are attempting to proceed towards randomness. That's the low energy portion of the system universally, and we have to oppose that with our own force and our own work to get that back to a state of order. And so randomness is its own energy component. We can actually quantify randomness as like an energy unit that's measured in joules per Kelvin. And so we can think about it and its contribution with enthalpy to the overall energy change of a system, and then relate those two things and their impact or change in a chemical system to this question overall of whether or not a reaction is going to proceed with or without external motivation, which we call spontaneity or spontaneous reactions. So we assign the variable S as entropy, and then we use delta S to think about the change in entropy, just like we've done with all changes so far. And so the change in randomness or entropy in a chemical system is going to be the final state minus the initial state, just like we've done before. So we could think about plotting S on an energy diagram and think about the final minus the initial to evaluate what the change in entropy is. for the system. So we can think about entropy just like we did with enthalpy, and its association with a change in chemical state or physical state. So we'll look at physical state first. Remember, physical changes are those that don't change the molecular identity. So the simplest one is always water, thinking about it going from ice to liquid water to steam or vapor water. Let's think about the change in entropy here. Think about the randomness of these different physical states. If you have ice here that's locked up in this perfect crystal lattice, so this is sort of the microscopic view of that if you were able to zoom in, look at how all these water molecules are oriented. They all have this structure where they are perfectly aligned in the physical crystalline state. And they can't move. They're locked in place based on some intermolecular forces that are holding them together. They're not covalently or ionically bonded, but there is an energetic interaction that locks them into place. They can't move, they can't rotate, they can't vibrate, they can't move in space throughout. They're just locked in that crystal. Is there much randomness in this type of arrangement? No. Crystalline states have the lowest entropy possible because there's no freedom for movement. Think about then the transition to the liquid state, this center picture. So in the liquid state, you've got more distance, greater distance between those molecules. They have the freedom to tumble and move through the solution, though they are still pretty intimately in contact with each other, which gives water its sort of viscous, pourable qualities that we know about it. So there's a greater degree of entropy here, meaning there's more randomness, there's more states that each of these individual molecules can exist within, which means if there's more states it can exist again, there's multiple probabilities for the arrangement of all these molecules in the water. There's lots of different iterations. And now think about if you add more energy to the system and you get the physical distance pretty far apart for these water molecules. They're no longer in contact. That's what steam is, or water vapor. And in this case, they have the highest degree of mobility. They can do whatever they want. They can rotate, tumble. They're not influenced by any other molecules. And so that's the maximum sort of entropy of the system. And this is just going from 3 different physical states, but I think it gives you an intuition for what molecular randomness can mean on the chemical scale. Let's think about this chemical example then. So we have this molecule here, there's this double bond, this is ethane. We can add bromine to this. This is a really common organic chemical transformation, and it's gonna combine these 2 molecules to this bigger molecule. What do we think with our intuition now of what molecular entropy is? Is the entropy going up or down? Is the randomness going up or down when you go from 2 gas molecules to 1 bigger liquid molecule? Well, hopefully both of those are pointing you to the direction that there's a decrease in entropy. We're starting with some level of entropy here, and we're ending at a lower degree of entropy. And this is actually a minus delta S in this case. And that's because you're going from 2 molecules over here, 1 and 2, to 1. So you're actually reducing the possible arrangements that these molecules can have because you're locking them together. At the same time, you're going from gas state, where molecules aren't really interacting with each other themselves, to a liquid state where they're condensed and they're interacting. So there's less degrees of freedom here. So this is a decrease in the overall entropy of the system. And remember, the universe wants to increase entropy at all costs. And so it's a little different than enthalpy, where we said a negative change was good. In the case of entropy, a negative change is bad. It's working towards destabilizing the system. And we'll talk about its contribution and how we weigh that against the enthalpy change of the system, because we could also compute what the delta H of reaction is for this. So how do we think about the delta H of reaction and the delta S of reaction, and how these 2 things work against or with each other to ultimately inform whether or not a reaction is going to be spontaneous? So that brings us to this concept called free energy. Free energy, don't get concerned with the name, it's not that important. Get concerned about what it actually means. And really, it's exactly what I just talked about. It's a quantitative way to relate delta H and delta S to this idea of spontaneity. And in free energy, we give the symbol G, and the change in free energy then is delta G. And that's quantitatively related to enthalpy and entropy through this expression, which is probably the most important expression in chemistry. It really tells us everything. This is the driving force for all of chemical reactions. So the change in free energy is going to be equal to the change in enthalpy minus the change in entropy multiplied by whatever the temperature of the system is. And this is typically in units Kelvin. Entropy is in units of joule per Kelvin, and enthalpy is in units of joules, and free energy is in units of joules. And so delta G is the proxy that tells us whether something is positive, or spontaneous or not. So if you compute this value, if you've got the overall enthalpy of the system, which again is really just the change in bond energies of the chemical reaction, and you've got the change in entropy of the system, which is the randomness of the system, and the temperature, you can compute delta G. And so delta G, for positive changes in free energy, we're going to consider this a non-spontaneous reaction. Non-spontaneous meaning we have to put some sort of force or energy or work into the system to get it to run. The opposite of that then, minus delta G, is a spontaneous process, meaning it's just going to work. Universally, it's going to go downhill from a higher energy state to a lower free energy state, and we don't have to do anything about that. Think about that as a ball just rolling downhill. It's going to go that way. Non-spontaneous means you've got the ball at the bottom of the hill and somebody's got to do something to get it back up. So this equation is the most important equation in chemistry, and this relationship is the guidance that we use to assess whether or not a reaction will occur or not without some external influence. So I like to think about this equation really as a weighing of forces. So you have your enthalpy, which is again the change in energy of bonds breaking and forming in a chemical reaction, and then you have the temperature weighted entropy, which means temperature just multiplied by whatever the randomness or the entropy change is. And these two things can work together, right? Because if your goal, if the universe's goal is to make this thing negative, because that's the spontaneous direction, then you can imagine these things can work together or against each other. If the delta H is negative, which means it's an exothermic process, so if you've got a negative delta H and you subtract a negative delta S, meaning a reduction in entropy, a reduction in the overall randomness, that means you're subtracting a negative value. And so this value can weight or overly weight this and yield a positive value. If that's positive, it's a non-spontaneous process. That would be working against each other. That would be enthalpy is good, it's negative, meaning you're going downhill in terms of bond energy, but it means you're also losing randomness in the system. That's working against the overall free energy of the system, leading to a positive change in free energy, which would look like this if this were G that we were plotting. Okay, that's working against each other. Let's think about working with each other. So what if you have a scenario where delta H here, again, we're pointing, this is referring to delta H on this sort of fulcrum here, they're balancing each other out. If we have a negative delta H, again, that's good, right? That's a net stabilizing force for the chemical bond energy of the system. We subtract then an increase in the entropy, meaning we're getting more random, then this becomes the subtraction of a positive value, which means the overall magnitude of this becomes more negative. That's working together to make overall a delta G that's net negative, that's spontaneous. So we could work against each other. These two things could work against each other. They could work with each other. We could also have a scenario where you have a positive delta H. That would be endothermic, right? So that would mean that the surroundings are getting colder. That's a net destabilizing force, right? Because that means we're going uphill in H, in enthalpy. So that's not usually a good sign. But we could subtract a value that is positive if we have an increase in our entropy. And if this term is bigger and more positive than this endothermic term, this can still be negative. And this is a really interesting situation because that means you have an endothermic process, a process that gets colder but is still spontaneous. Where do you think you'd find a commercial or practical example of that type of process? Well, that's a cold pack. Right? If you've ever used a cold pack before, you smash two portions of the pack. Looks like this, and there's a little bag on the inside. You smash that open, those two fluids mix with each other. This thing gets really cold, so the temperature plummets, which means the enthalpy is actually going up for the actual system. But at the same time, the molecular randomness is also going up, which means that these two things are working against each other but in the opposite direction, and we end up with a spontaneous process, meaning the reaction just runs without us having to do anything about it. So these are sort of the three examples, and it's really helpful. We're not going to do anything much more with free energy aside from thinking about spontaneity. So is something spontaneous or not, which is really based on positive or negative in terms of delta G, and then also thinking about these different scenarios. So what happens in these different cases? We have an exothermic reaction with decreasing entropy. That's a non-spontaneous process. We have an exothermic process with an increase in entropy. Well, that's a spontaneous process. And then we have this other scenario where we have an endothermic process and a net increase in entropy, and we have this spontaneous process. We could have a fourth version here if I sort of scroll up, where you could have the endothermic process, again, increase in delta H minus a decrease in entropy, and in that case you end up with a non-spontaneous process as well. So I'm going to want you to think qualitatively about these things. I could ask you scenarios where either one of these things are changing, and then I ask you to speculate as to whether or not the process is spontaneous or not. Or I give you delta H and delta S in temperature and ask you to compute those values yourself. Okay, so a quick example here. We've got this reaction which we talked about in a previous video. This is the reduction of water with carbon to make hydrogen gas, the industrial production of hydrogen. And with that, we've got these two parameters here. So we've got the change in enthalpy as positive, increasing 131 kilojoules for the reaction as written. And then we have delta S for the reaction as plus 134 joules per Kelvin. So let's think about this in terms of these values. Let's just qualitatively assess this first. So is this endo or exothermic? Well, to answer that, hopefully you're looking at the sign of the delta H. We know that the H here, starting at carbon and water, is going up to CO and H2. That's increasing. So we've got a positive delta H, which means there's heat coming in from the surroundings to the system, and we call that an endothermic reaction. Okay, that's a good step. Is this becoming more or less random in the way that this works? Well, even if we didn't have delta S here, I could ask you that question, and you could conclude that we're going from a solid, purely crystalline, this is graphite, right? Solid carbons, pure, it's like the graphite in your pencil, perfectly organized carbon, and water as a gas, to two new gases. And so two new gases, even though the number of molecules are staying the same, the two new gases indicate that there's more molecular randomness or freedom for movement when you got two gases instead of a crystal and a gas. We also could look at this and say, well, S is going up here, so we're starting at carbon and water, and we're ending up here, so we end up with a positive delta S. So what about the overall delta G for the system? Well, delta G is going to be delta H minus T delta S. Of course, we're going to need to know the temperature of the system, and the temperature may be the factor that changes where or when this is spontaneous, right? And so I could give you several different temperatures, and I could ask you when and what temperature is this a spontaneous reaction, and you would compute this. Whenever it's negative, you could say that that was the temperature at which it was spontaneous. Another way to compute that in this particular example would be to ask yourself, at what temperature does this become spontaneous? Well, what would that look like mathematically? That would be the point at which delta G goes from a positive to a negative value, which means it has to go through 0. So we could solve this, set delta G equals to 0, and that would allow us to rearrange this equation to say T equals delta H over delta S. If we have this value, this is, again, this is at delta G is equal to 0, because that's when you're transitioning from non-spontaneous to a spontaneous process, right? You have to go through 0 in that case. So you could input these two values here, and if you do that, you can check my number here. I'm sort of doing this off the top of my head. We'd get a value of roughly 978 Kelvin, which would equate to about 705 degrees C. 705 degrees C would be the point at which this reaction becomes spontaneous. In other words, you put this stuff in a vessel, you've got some carbon in here, and you've got some water in here, and nothing's happening, right? No reaction is running, because it's not until you heat this system up to 705 degrees C does this reaction start to run in this direction spontaneously.